linear regression, we also will review one other classifier which we have already studied, Bayesian. So why I'm saying this, because today when we're doing a data set, we'll do compare both. That's when you start getting into your experimentation mode, where you are equipped with multiple tools, whether you have a Bayesian classifier or whether you have a linear classifier. You'll try to look at both as a tool and try to compare. As and when you get equipped with more algorithms, we'll do this comparison, because otherwise you will be boxed to think that for this example it is this classifier which works. It doesn't work like that. So as I said, Bayesian theorem is about understanding how you can derive the potential probability of a particular cause having observed a certain effect. So there can be multiple causes for a particular effect, and you a priori, means before the event itself, you know what is the normal scenario probability of each of these causes occurring. That's what we call a priori probabilities. Then we also know if the cause had occurred, what is the probability of that effect for each of them. By that, we want to do a diagnosis. Diagnosis is a very common scenario in machine learning, where you observe a symptom or an effect and you try to infer what is the maximum likelihood cause. Suppose we have detected that there is heavy bleeding reported by a person. We could have several kinds of causes. It could be related to cancer, it could be related to hemophilia, it could be related to maybe some other internal bleeding. But if each of these causes, historically, we know the probability of A, which is observing heavy bleeding, or that given, say, cancer, given, say, hemophilia, or given internal bleeding, then we also know normally how many people get cancer, which is a priori probability, or how many people get hemophilia, how many people get, say, the internal bleeding scenario. Then, having observed in your case that there is a heavy bleeding, you can derive what is the corresponding potential maximum likelihood cause, and then you derive that based on Bayesian theorem. So Bayesian theorem is very simple. It says that having observed an event A, which is like in this case observed cancer, sorry, observed bleeding, what, let's say we have B1, B2, B3. So we want to find out what is the potential that it is caused due to cancer, or the potential that it is caused due to hemophilia, or potential caused due to internal bleeding. We can take this particular formula, which is basically very intuitive. It says that if you take absolute probability of cancer times if what is the probability normally of bleeding given cancer, and multiply that across all the three, add it across all the three. So similarly, the worked out example here was about if you have a wet garden, you have scenarios whether it's rained or not rained. You know, normally 40% times it rains, 60% it does not rain. But if it has rained, then wet floor is caused 90% of the time, PA given B1. 20% of the time, if it does not rain, then also it is wet floor. Given that now that you observed a wet floor, what's the probability that it has rained? It is 75% by going by this formula. You get 0.9, 90% of conditional probability of wet floor given rain times absolute probability of rain. That is the probability of it having rained and it having wet floor. So you got to understand that whether you talk about probability of A intersection B is same as probability of A given B1 times PB1 or probability of B1 given A times probability of A is very important. Both are equivalent because both of them talk about the probability of simultaneous happening of one of the cause and the effect. So it is a commutative property. Now, how do you use that in case of a classifier? What we try to do in the classification, as I said, right, there are m classes into which you want to classify the data. Typically, you will have multiple attributes, right? You may have one. In our case, we talked about actually, in our case, we actually talked about only two, which is have cancer, nor have bleeding, no have no bleeding. So we could have two. Sorry, that's the observation. That's the observed classes. In this case, we only talked about one cause, which is basically saying that what is the probability of all three of them to, sorry, either it's a cancer, it's a hemophilia, or it's an internal bleeding. But we talked about only one cause. Sorry, one cause means we're talking about only one variable. But it's possible that you have multiple variables influencing. We think about a scenario like you also look at something like age. So you have a combination of age and potential disease. So if you say you have age less than 30, age greater than 30 but less than 50, then age greater than 50. That becomes a second variable which influences. But in Bayesian classifier, the beauty of Bayes theorem and the advantage of the theorem is that we can work with individual conditional probabilities of each variable independent of the other and just multiply the individual classifier probabilities. That's why if you have observed a certain instance which is for the future, which is collection of variables of values x, and you want to find out the potential cause, then you multiply the potential of the output variable given the current given the current classifier for each variable, and then you multiply them.